Okay, hello everyone. We're gonna start with the session. I don't think you'll need coffee because this session is extremely exciting. But if you do, you have a few seconds to do that, and also to respect all those online. We'll be starting soon. We have two panels, one after the other, on the same topic, which is the use of AI for Earth observation for food security. We have the first panel is 3 people, and it's such a personal and professional pleasure to introduce this panel because I have worked with each of them in previous positions, so it's such a nice coincidence, or maybe not a coincidence, that we are together to talk about these issues. In the background, you know there is a lot of talk today and these days on AI, but I'm also aware that it's a much wider space, the use of AI, and there could be a substantial gap between what is possible and what is used, right? So this session is about, as I was saying, the use of artificial intelligence with Earth observation for food security. And the 3 panelists is 2 from the private sector and 1 from academia that also comes out from NGO before. And in the next panel, we also have the private sector. So it's bringing new voices to our session, our event today. So first, we're gonna hear for 15 minutes each, and the first one is Raul from Microsoft AI for Good. It's great to have you here. I think you have 15 minutes and you have the slides there. We will have the questions as before at the end of the 3 presentations, and then we have the second panel and questions for that one.
Hello?
No, still not. Maybe press a button somewhere?
No, there's no button over there.
Okay.
Yeah.
Is it working?
Yeah. Oh, now I can hear myself. Hello, everyone. Good afternoon, and good everything to everyone around the world. It's a real pleasure for me to be here. This morning's presentations were incredible. I learned a lot, and it turns out I probably have more questions for all of you than you'll have for me. So we'll get to those. But first, I want to introduce who I am. I'm from Microsoft. We have a lab in Microsoft called the AI for Good Lab, and I am the deputy director of that. I run the research science division. Who we are, we were created by Microsoft to address issues that people may have with AI. If you remember, AI is going to take your job. It's going to start World War III, etc. So the AI for Good Lab, our mission is to avoid those things and show you AI can be used for good things. We come from many different countries. We focus on real-world impact and open source technologies. So we are a non-revenue generating part of Microsoft, which means I'm not trying to sell you anything. And we are committed to doing everything we do, we make open source. We don't hold on to any IP. We give the IP to our partners. Because of the focus we have now on climate change and food security, we did open a team in Kenya, and I'm quite aware that every presentation has mentioned Kenya so far. So we have a team in Nairobi, Kenya, and we're opening a hub in Egypt as well to focus on African issues of food security. We're also focusing on public health and biodiversity. So just to give you an idea, these are the things that my team works on. We do work on disaster preparedness, like the aftermath of earthquakes and cyclones. We look at population and migration, especially climate-related population. Food and water security is a fairly new addition to our portfolio, and also sustainable development. We'll obviously be talking about food and water security here. And this slide, I don't really need to talk very much about. I think everyone agrees. we're focused on climate change adaptation. It does not preclude mitigation. And we know that we're not going to hit the goal of 1.5 degrees. We know that there's going to be, the poor are going to suffer the most from all this. So my lab has started working, my team has started working on these issues fairly recently in the last few years. And what we've found is that it's really it's really our partners who make this possible. What I bring to the table with my team is AI expertise. And we can bring you experts in machine learning. We can bring you research level, world-class research level work in all sorts of machine learning technologies. What we are not is we're not experts in anything except that. So we're not experts in health. We're not experts in food security, which is why it's fascinating for me to listen to people today. The way we achieve our impact is we partner with people, with organizations that have a proven track record, people who can take our technology, take it to the ground, and actually do something with it. So one of our biggest partners for high-resolution satellite imagery is Planet Labs. So we have a really good partnership with them. They provide us with high-resolution imagery when we need it for, let's say, events happening in anywhere in the world, but particularly Africa. And of course, we can use Microsoft resources like Bing and Azure. But there are other partners that I'll be talking about, and you'll see that some of the use cases I'll be showing you, they were done with partners, and that's the part I want to emphasize, that without them, we couldn't be having any impact. The types of food security models with our partners that we've found that we need to create are ones that have been talked about, like Inbal from NASA Harvest talked about some, and everyone's been talking about some of the models that have been done. So land use, what's the land being used for? It's used for land cover mapping, like what are the crop types, irrigation use, basic water management. So those are the types of models we bring. Early warning systems. The IPC, food security classification that FAO uses, the World Food Program uses, the World Bank uses in the graphs that you showed earlier. Crop diseases and famine. Can we anticipate famine with that kind of data? Disaster management, we're building a disaster management toolkit so that if there's an earthquake, if there's a disaster somewhere, someone can use that toolkit to immediately assess using imagery, satellite imagery, to a very fine level, to a block level, to a street level, where the disasters are, where the buildings have fallen, where to send teams for assistance. Now, for all of these, we've also found that we need some ancillary models. We need to know where the populations are. So we need some really fine gridded population maps. I'll talk a little bit more about that later. We also need poverty mapping, like who's going to be suffering from these events, including food security. And another thing I'll be talking about is renewable energy trade-offs, because you could use land for agriculture or you could use it for energy. Is there a compromise? So let me talk about food and water security. And these are some of the partners we work with: the Nature Conservancy, CETRAD in Kenya, the US Geological Survey, and of course, Planet. And just an example project, and I'll use Kenya as well, regenerative foodscapes. So the Nature Conservancy has this concept of regenerative foodscapes. And farming on the north slopes of Mount Kenya is where a lot of farming happens, but it's very inefficient. There are rivers, there are streams, But irrigation is very inefficient, and what they want to do is figure out where are the smallholder farms, where are the larger farms, how is the water being used, can we map all that? And how do we then take that data to the ground and have people on the ground go to these farmholders, show them that this is what you should be doing instead. That's the idea that the Nature Conservancy has been working on for years, and now they're pushing it forward with satellite data. We started with Sentinel data, but we found that Sentinel data was too coarse for what we wanted to do, like especially if you're trying to find smallholder farms, you need high resolution data. And so we use planet data now. We use quarterly, their PlanetScope quarterly planet data, which gives you a resolution of less than 5 meters. Even that might be too much. But this is something we found that we needed to do here. It's something that I question, that how generalizable this is, because yes, sure, we get planet data easily. What about the other people? Like, do you have $1 million to spend? Yeah, sure. But that's something we need to discuss, and that's something we're very concerned about. So just a little bit more about the Nature Conservancy project here. It's called the Central Highlands Ecoregion Foodscape CHEF. It's an agricultural strategy that they're trying out in Kenya and a few other regions around the world to see, can we work with agriculture and wildlife conservation and conflicts between various land uses? Can we resolve them together? So I want to talk about the ancillary models as well. We use poverty mapping in Zambia to identify regions of food insecurity, because when there's an event, it's the people who are poorest who will suffer. So the Zambian government is very interested in mapping poverty rates across the country. We also create fine-grade population maps, and this is with IHME, the health metrics organization based in the University of Washington. What we do is we create very fine-level maps. And why do we need to do this? Don't they have census every 10 years? That's the point. It's every 10 years, sometimes never. So we use satellite imagery, and we kind of use an arguable way of doing this. We look at buildings. We look at building tops, the roofs of buildings, and from there we can get a very good idea of how many people are living there. I was a little skeptical, but when we achieved really high accuracy with that, I was convinced. So we will be releasing a global population map at a very fine grid that can be updated almost daily for people to use. And again, like I said, can we make this open source? Can we give the IP to someone? We don't want to hold on to it. Then there's Global Renewables Watch. This is again with the Nature Conservancy and Planet. We're building another dashboard which uses Planet satellite data to figure out where in the world there are solar farms and wind farms. So you don't have to wait for on-the-ground reports. You can't hide from the satellites. We know how much satellite, how much solar ability you have, how much wind power you have. And I encourage you to go to globalrenewableswatch.org and sign up for it and see at a very fine resolution where these are. Now, these are, I'll skip that. These are all projects that, again, we are creating them, but the questions I have is, when we create these things using satellite imagery, and I've been asking a few people about this, what is the benefit that you don't get from other data already? If you're creating country-level maps using satellite data, wouldn't the countries already know that they are in a certain state? And if you're creating something that can be used at a lower level, isn't it too expensive? Like if you want to buy, if you want to get annotations to corroborate with ground data, if you need the low-level imagery, the high-resolution imagery that we've been using, that's very expensive. But what we want to do on our part is to, first of all, to figure out with your help, how do we open source this? Well, we know we put it on GitHub, but that's not enough. Who can we partner with to take this global? Because we are a technology company, but we're not a, we don't do these things naturally. So those are the questions I have for you, and I'd be happy during the question answer time to discuss those. Thanks.
Thank you, Raul. While the next presenter, which is Rhiannon Price, Chief Strategy and Innovation Officer for the Global, prepares her PowerPoint, I should mention, Rahul, that even if not Q&A, they released a database of ground truth for buildings called RAMPS. I don't know if she's going to talk about it or not, but I wonder if your accuracy would increase based on that.
Thank you, Bruno. Thank you so much for inviting me. I'm really pleased to be here. As Bruno mentioned, my name is Rhiannon Price. I'm the Chief Strategy and Innovation Officer at Dev Global, which is a global consultancy that really focuses on using geospatial technology, especially Earth observation, for humanitarian and sustainable development outcomes. I think today what I'll talk about is a little bit different perspective, I think, than some of the previous speakers in terms of seeing our impact from space, not only in terms of using Earth observation satellite imagery to have an impact, but actually using the same technology to understand what's working and what isn't working, even in places where we haven't actually used satellite imagery as an intervention, and how is AI actually accelerating that, and where should it be accelerating that? So to start, I wanted to kind of pose this so what question, and I know I'm preaching to the choir here, and I'm not going to extol, all the value propositions of using Earth observation for food security, but I think important considerations for us when it comes to impact, but also related questions around sustainability, accessibility around these are about finding the combinations of these value propositions when it comes to applying satellite imagery in the context of food security monitoring. And what I mean by that is, where the coverage and where the repeatability are there, are you also going to get the affordability over time, and what is that tipping point to get there? Rahul made a really great point of, especially commercial imagery is expensive, but there is always a tipping point in which that expensive imagery becomes less expensive than the alternative, which in a lot of environments are costly ground surveys, sending folks out into the field. And in some cases, those simply aren't options, right? Especially in fragile contexts. And so I think we always have to ask ourselves the so what very early on. And I think, Alex mentioned this in his presentation, the so what also begets questions of availability, accessibility, those 5 A's that ESA likes to extol. I won't go through all of this because I think this is really, again, preaching to the choir a little bit in terms of we've got data, where we're applying it, and what outcomes and impacts we want to see. There are a myriad of ways, right? There are lots of ways that you can mix and match these things of what kind of data, how you're going to apply it, what kind of outcomes you're looking for. And up until this point, I would say the landscape has been kind of a free-for-all, right? Let's try all the methods, let's see what works. Really, we're trying to build an evidence base. But today, the exciting thing that we're seeing is there's starting to be consensus in the community around which methods make most sense for which impacts. And granted, there's a lot of variability there, which we'll talk about more. But I think this is just kind of a powerful lens to say, this is the realm of things in our toolkit. What do we need to be considering? And this is really just the tip of the iceberg when it comes to what we can actually derive and sense remotely. What does this mean, though, in terms of food security? Well, for the community, you'll see here some of the data that we found. This is part of a study that I supported with Caribou Space for the UK Humanitarian Innovation Center. Really, when we looked across, I think, 500 plus applications of how Earth observation was being used, we saw that there's a lot of interest in terms of crop yield and productivity forecasting. unsurprising, right? That's kind of the Shangri-La of what we're trying to do here, especially at scale. But then the next orders of magnitude drop off pretty quickly, right? Natural resource mapping, especially in these questions of doing climate-sensitive agriculture, mission critical, but it's a lot of times siloed, especially away from considerations of yield. Same when you talk about early warning systems, which unto themselves, of course, necessitate some yield and productivity forecasting, but need many different parts to actually be, a warning system. We also found through this landscaping effort that a lot of these applications are concentrated in Africa. So where are we seeing uptake of Earth observation applications? Africa is one. Asia quickly follows, but drops off is about 25% of those 500 applications that we saw. Why, I think, is an interesting question. I think a lot of times it's around kind of international agendas and not necessarily in terms of where the impact itself needs to happen, but that's another question. And then we're also starting to see through this report that there are kind of emerging uses. And that's where I was much more excited, is the bottom of this list, I think, are things that we really need to watch and where the evidence base is really being built right now and where we can move the needle in terms of where these technologies are applied moving forward. I had mentioned in terms of the kind of consensus that is happening around some of the methods and approaches to getting to food security outcomes, to actually try to use these technologies. And I think this is a really fantastic summary, and this is from a team out of Stanford. David Labelle and that group created this as part of their kind of series of work. And what you're seeing here are actually where vegetation indices, for example, are the most applicable and helpful in terms of identifying or determining things like crop type. And having this kind of understanding, I think, is mission critical. One, because now we need to start to automate some of these things. And this is where the power of AI is especially exciting for folks like me who want to understand the art of the possible. You can also see where there are multiple options across this. So for drought, for instance, there are a number of Earth observation derived data layers that can be really helpful for drought. And so the question there becomes, in what context and what conditions do I want to use which Earth observation inputs? And I think the short list over here are where we've already have this incredible evidence base of where satellite imagery are particularly helpful when it comes to understanding things like growth stage, crop area, et cetera, which are in many ways the building blocks of food security monitoring. As I mentioned, though, the application side is only one part of it. The kind of impact evaluation side is another area in which Earth observation really, really shines. And it shines, I think, in ways that are a little bit complementary to some of the kind of value propositions and strengths of Earth observation that we've talked about. And I'll say that because, one, it is, in one sense, a great opportunity to have remote sensing to be able to actually understand what's happening on the ground in places that you simply can't access, but also where it's just unethical to use RCTs, random control trials and things like that, because of the nature of what you're looking at. In a lot of cases, it's also cheaper and faster than conducting an RCT, and not to hate on RCTs, which I'll talk about in a minute here, but I think that is a really powerful thing to consider in terms of just understanding what's working on the ground. Having the kind of immense archive that we have right now, but also the ongoing collections, means we can not only understand trends over time, even outside of the actual intervention lifespan itself, but now we can actually start to understand what that trend might be moving forward and observe it as well, which is very powerful, alongside the kind of question of the spatial dynamics, right? Which, of course, imagery and EO are really powerful for understanding. This might be happening over here in Kenya, but what is happening in the rest of East Africa, in the Horn of East Africa, where a similar drought is happening, right? And so I think that is also another way in which Earth observation is just incredibly powerful. In terms of kind of the levels in which we analyze what's working and what's not, that's also where the fidelity and the resolution of what you can do with Earth observation really shines. So you're talking about, we can analyze things at a project level, where your investment, let's say, is over a certain 5-year time period. We can look there and see what is actually changing on the ground. Or we could also do it at a portfolio level, which is in some ways even more powerful, right? So we've made a series of investments in these countries, in this region. Have we moved the needle? Let's see. Let's understand what yield and productivity look like. Let's understand what adoption looks like, all the things that we can see from space. And last but not least, of course, not to hate on RCTs, the power, I think, of having remote sensing complementing things like household surveys, randomized control trials, things like that, is immense and something that we're really just starting to explore. And I'll show you in a case study of what we're doing, why we're really focusing on that. So Dev Global, we're a part of a consortium with a few other groups on an initiative called GeoField. Data at William and Mary are leading the consortium. We're part of it with Mercy Corps. It's funded by Gates Foundation. And the premise of GeoField is really to accelerate these kind of climate-sensitive impact evaluations using Earth observation for agricultural outcomes. And so what we're doing as part of this is kind of twofold. We have a research agenda on one hand, where we're really trying to push the envelope in terms of how satellite imagery and Earth observation are actually used to understand impacts and learn and evaluate what's actually happening, but then also build a community of practice. And the approach we're taking for that community practice, I think, is really important and salient for this group of, we want to build a kind of community of communities approach. So we want to bring in the food security experts, we want to bring in the remote sensing experts, we want to bring in the evaluators, we want to bring in the funders, and really knock down our silos, because we already know that these communities exist. We just don't always necessarily interact with each other. And so much of what GeoField is doing is not only pushing the needle in terms of the cutting edge research and applications of the technology, but also starting to knock down those silos so we can continue to do that once we actually prove out what works here too. As I mentioned, part of GeoField is really about kind of one facet is research agenda. So we're just kicking off. It's a 4-year program, so we're really just getting started with the subset of rapid use cases. And there are 4 that we're really focused on in partnership with groups like Mercy Corps, ERI, FAO, even national partners like the Niger Ministry of Environment are also involved. And a lot of these are looking at interventions that are, at this point, historic. They happened years ago, where Earth observation wasn't used to understand the impact. They used more traditional methods. And so we're taking an ex post look to say, does Earth observation come up with the same conclusions as the impact evaluation that happened without Earth observation? And the results have been really powerful, and I'll give you one example here. So this is just one of the rapid use cases, and we're just really starting this right now, that's looking at water conservation in Niger. And so this is really what the remote sensing is trying to do, is proving, are farmers adopting demilunes, this water conservation technique, and are we seeing the same kind of outcomes that were expected from the original impact evaluation from the Earth observation data? And what they found when they conducted the original impact evaluation, that farmers, over 90 percentage points, which is really impressive, adopted demilunes just based on training alone. And they were looking at, was it training or was it cash transfers or combinations of the two that actually got farmers to adopt this method? And really what they found was training was all that it took. It didn't take any cash transfers. That was a negligible difference. And what they saw then from those farmers who adopted demilunes was that adoption increased agricultural output, that it reduced some of the land degradation that had been happening historically, and that it led to spillovers in terms of other good agricultural practices, but also spillovers in terms of other indicators that we are also now observing from space. So what we're doing as a geofield team are actually working with the implementers behind this intervention to say, can we kind of confirm what the what the impact evaluation saw years ago? And also, is this a more effective way of doing an impact evaluation where we can actually continue to monitor moving forward what's happening in Niger, what's happening with demilunes, even outside of the few years that this is being funded as a kind of donor effort. And so Niger is just one example of the few that I saw. We're also looking for longer term use cases. So this is a call to action, especially for this community, that if you have an intervention where you would like to see a kind of geospatial impact evaluation conducted, definitely talk to us, because we have the resources and the expertise to partner with you to actually do some of that work over the next few years, and would happily talk to anybody about what we're looking for in terms of those next series of case studies. Last but not least, as I kind of wrap up and really kind of revisit where is AI in all of this. So as we talked about, there's a growing range of applications. There's a growing even evidence base around that. And I think crop insurance is a good example in terms of where is remote sensing actually helpful for crop insurance programs. And we're starting to see around index-based approaches where it's helpful around losses and improving methodologies, and also just reducing the cost of the field work that has to happen to actually do those insurance payouts. And then another area, and we've seen a lot of this today already, is around reproducible indicators that can scale, right? So a lot of these kind of, especially early warning systems, are using these major indicators that are trying to be comparable across countries. That is a perfect opportunity for AI to be really disruptive. One, in terms of just shortening the time frame, but also doing it in a way that actually accounts for the diversity of what we're seeing between the conditions and the geographies, et cetera. And then last but not least, as I mentioned, increasing the evidence base, and this whole idea around impact evaluation is another area in which we have so much room to explore, because more often than not, remote sensing, Earth observation can actually report on at least, as we call it, one headline outcome. So even if it says something as basic as NDVI and looking at that, that's another powerful complement that we, by and large, haven't had before when we've been doing crop cuts and things like that that are really high touch in the field. So of course, opportunities for AI across all of this, but even more so, as speaker said earlier, there's an opportunity for the validation and kind of the local expertise within all of this and that kind of leadership, which certainly can't be forgotten and is the other kind of, I think, leg to the stool of having not only the remote sensing, the field data, but also having that local expertise to make it all kind of come together. So with that, I will wrap, and thank you so much.
Thank you, Rhiannon. So we have now the third and final speaker of this session, which is Hamed, Director of the Center of Geospatial Analytics at Clark University and the outgoing Director of Radiant Earth. If the slides work. There we go.
Okay, it works. Good afternoon, everyone, and evening, morning to our online participants. Thank you to the organizers inviting me here. So I am at Clark University, directing a new center called Center for Geospatial Analytics. Very appropriate to this session, so excited to be here. Previously, as Bruno mentioned, I was at Radiant Earth Foundation, leading the organization for a couple of years, working at the intersection of AI and geospatial, basically, and particularly around the question I was asking in the morning around benchmarks, training data sets, how we can have a better community standard and kind of procedures for publishing those. Today, I'm going to talk a little bit about what AI has enabled us to do, picking up on examples, going deep into one specific example of crop mapping in Ghana, so not Kenya, and then coming back on where I think we should go next. What are the things we should keep in mind as we move forward? So stepping back for a second, let's not forget there are three drivers of this ecosystem that implicitly everybody has talked about them so far since the morning. But that is one, data acquisition. So we are measuring and capturing imagery at a rate that is unprecedented in the past. And not just in terms of temporal frequency, spectral frequency, modes of observation, which is significantly different than even 5 years ago. And it is going to explode even in near future with all the new commercial imagery coming up, which many of them also open up to applications we are interested in. So it's not like it is necessarily paid. Not that that is wrong, but I mean, there are also open data sets available to us. How we access data has significantly changed. Data is moving to the cloud. APIs are very different. Computes are closer to the data. So we can do things much more efficiently. And of course, AI and advanced analytics. So things have enabled us to explore questions, find patterns that were kind of, I would say, impossible or close to impossible 10 years ago. So let's not forget about these three pillars as we think about AI applications in our domain. An example from NASA Harvest Team. So this is a country map of croplands in Togo. Early days of the pandemic, Togo's government was interested in the cropland map in 2 weeks, and we have no data. They came to us, but we were at Radian. We're like, this is not us. We don't have the bandwidth, honestly. So NASA Harvest picked up the project. In 2 weeks, they delivered a map of croplands in the country, which was specific to the use case that, hey, we need to do this rapidly because we want to know where are the farmers, what is happening to them because of the COVID, basically lockdowns and everything, how this is going to impact the end of growing season production, and what is the impact on the livelihood of farmers if we should do any investment or subsidies. And AI was able to do that because there was some existing labeled data, the team generated new things, and they could scale it up quickly and generate that. Another example, close to agriculture, not exactly more on biodiversity, but mapping individual trees in the West African Sahara. So again, using very high resolution imagery, in this case Maxar imagery, and AI, they have been able to detect 1.8 billion individual trees. These are not forested areas. These are individual trees, which are very key to preserving biodiversity. Again, being able to do this thing is because we have very advanced analytics close to imagery and everything. So with these two quick examples and many more that you have seen in the morning, I want to claim that what AI has enabled us to do in the last several years is, first of all, doing things at a scale, which we have been doing in different perspectives in the past, but it is now much more scalable. We can do that rapidly and on demand, particularly if we have some initial data or a pre-trained model or some level of that, we can do it rapidly. And particularly if you have the right model, you can run inference very quickly. I will show in an example next. We can do things more efficiently. This is my claim. I'm a remote sensing scientist by training myself. And things we were doing 20 years ago and how we are doing them now, they're computationally more efficient, significantly more efficient, because traditional remote sensing would be an inverse modeling, which is very expensive to solve computationally, and AI is really helping us to do that more efficiently. More accurately, let's talk about that. We will get there. I don't know. And that depends on the application, and that's why I have the question mark. So this is an example from one of our faculty members at Clark, which is an annual country-scale field mapping of agricultural fields in Ghana. So it uses planet imagery, typical pipeline of machine learning. You have some pre-processing of imagery. In this case, the project was implemented in 2018 initially. Without the planet NICFI data being available, they generated their own composite maps. Then they did a good amount of labeling using a team, looking at imagery, building a lot of kind of uncertainty and modeling into that. A very active learning kind of methodology in terms of machine learning, so having a good accuracy, and then generating the segmentation map. I'm doing that. This is a country map of croplands in 2018 across Ghana. You can see some examples from different regions. An accuracy metrics report, again, at the scale of the country, doing around 80% accurate. Because I think Rahul mentioned about the cost. This is an example, actually. I had these numbers. So this country-level map needed around 4,500 labels, which is not few, but still, you can do that reasonably, kind of, I wouldn't say cheap, but with a reasonable cost. And when you run inference, the cost is less than a cent per square kilometer. So when you train the model, don't get me wrong, that is a cost. We didn't account for that. But when you're running inference, so hopefully you have a good map, you can run it more frequently, it doesn't cost us that much. But then issues come up, and that is, this is 2018. Let's go to 2019 now. And now you have NICFI data, so you apply, and you start seeing very weird patterns in your data. That is what we call in AI domain shift. So imagery has changed, but it is the same landscape. So what went wrong? So AI is good, but you can run into problems. And that's what I want to talk more when I get to where we need to go next, which is we need to do a little bit of adaptation of the AI technologies, not just adopting it for our technology. And this is what this team did. You can see progressively, I don't want to get to the weeds of AI here, but adding a lot of what we call regularization, working on the model, they were able to get a much better accuracy for 2019 using the new imagery from NICFI, basically, and continuing to 2020, 2021. So if we know how we handle AI, we can adapt it for our domain and solve many practical problems in our field. So, and this is what I want to argue in this slide. So can it address food security? Very broadly speaking, I don't want to get to, is it cropland, is it crop yield or whatever? Yes, but we need to do a couple of things. One is, as I said, we need to adapt this, not adopt it. And this is, I think, one of the mistakes some of us make in the community. We just assume AI is off the shelf, we apply the model, we just want to get some results. Our data, our imagery, our ground reference, our domain problem is very different than the language data, the computer vision data. Even if it is imagery, it is very different, and it has very different properties. So we need to fuse those into the design of our AI systems to make sure we can benefit the most. We have been talking a little bit about who we are building these tools for. I think that comes in particularly when we talk about validation. Who is the end user and what is their use case? Then let's talk about the evaluation metric and the evaluation approach. Are we talking at the country level cropland map, or we are talking at the field level precision agriculture kind of monitoring system? These two need very different evaluation data, very different evaluation metrics. And sometimes we just mix them. So we need to be very specific at the beginning of their project design. We need more transparent and I would say reproducible pipelines so we build more trust. The better we share and we talk about how we do things, the end user will build more trust. The same way that an extension officer knows how their officer goes on the ground and collect data, they should also know, okay, this user that claims they have an AI model doing the same prediction for me, what is their pipeline, and building basically more trust, working with the end user. Increasing, we talked about benchmarks, geographical diversity of these training data sets, and people. So the people who work on these problems should be more of the problem owners themselves than just everybody else who feels this is a fascinating problem to work on. I will talk a little bit about the data in the next slide. Of course, responsible AI and including fairness and inclusivity. Are we allowed to monitor a farmer's field from 1,000 kilometers away from our Earth? I don't know. Maybe we should think about that question a little bit more. But we need more discussion around those angles. My answer would be yes, but I think it needs a broader discussion. And not to forget about our changing climate. Anything we are building today, it may not be applicable 5 years from now, 10 years from now. Raul mentioned about adaptation versus mitigation. We know it is happening. It is already here. So we need to think in terms of designing our AI systems to take into account our changing climate. About the benchmarks, since I have been at Radian, I should talk about this. So one of the things we established in the last couple of years was investing in curating and generating what we call representative training data sets. We also worked with Rhiannon's group at Dev Global on the RAM project that Bruno mentioned. So we established this repository called Radian ML Hub, which soon is going to morph into Source Cooperative, again, another expansion of that. So people can trust the data that they access. So it's an open repository specifically for geospatial training data. You see a map of where we have data, and the numbers represent the number of training data, and particularly skewed toward the developing world, because that's where there was lack of data. And it is operational. Anybody can access, self-service and open source. It is, as I mentioned, expanding to new sources, but we need more of these initiatives and also better incentives for people to publish their data. This is an AI session, so I would like to mention another angle we worked on, and that was exploring the role of synthetic training data. In some applications, yes, you cannot go and collect data on the ground. But we had this application at Radian, and all these images that you see are synthetic satellite imagery, not real satellite imagery. On the first row, you see pasture, cropland, forest, and airband. This is in the US, because we had good data to train that model. But then we went to South Africa and basically fused a set of wheat synthetic training data into a crop segmentation model, and we saw a significant improvement in terms of crop classification, just wheat versus no wheat, basically. This was a project funded by the Bill and Melinda Gates Foundation. So there is a role for exploring these innovative AI tools into how we can solve our problems, which is lack of benchmarks and training data sets. I couldn't not talk about foundation models. So where we are with that, I mean, we had again the question Ian asked in the morning, is this gonna help us? So just some background for those of you who may not be familiar. What is foundation model? So as you have heard, for each application in AI, we build an end-to-end model. We have some training data, we have some source imagery, we build the training data, we train that model, we have all the coefficients and everything, and then we run inference for that, whether it's crop classification, crop yield, land cover classification, water segmentation, everything. Foundation models, which is what is behind the ChatGPT of the world, are learning from the imagery itself in our case, without any labels. They are self-supervised. So they learn pattern in the data in the first place, then you fine-tune them for your application. And they have been showing promising results in the language model, to some extent in the vision. We are working now on a project as part of a consortium with NASA and IBM to see, is it useful to apply this in geospatial data? So we are very foundationally asking this question and hypothesis, is it worth it to do? We are not saying it is. The way we are doing is that IBM is training a foundation model on HLS data. Some of you might be familiar with that. It's the Landsat Sentinel harmonized data set. You get an imagery about 2 to 3 days globally at the 30-meter resolution with the same spectral frequency of Landsat or Sentinel. It is now running over the US because that's where we have more data to validate our assumption. Downstream, we are working on 3 examples. One is crop segmentation. So we are using USDA's crop layers to see, can we do crop segmentation with this foundation model more efficiently than training a baseline model, which is end-to-end supervised. Efficiently means to be more accurate, needing less training data set, and potentially computationally more efficient, because your foundation model is trained once, the fine-tuning might be cheaper for that. One on land cover classification, and one on actually gap filling. Can we get rid of these clouds in our imagery? So we are trying those 3 downstream applications. I don't have any results for you, but we can chat more. This is really early days of the project now. But that's where we think we should test this technology. Again, adapt it for our domain, fusing in the temporal dimension and see, does it work or not? And with that, happy to take any questions. Thank you.
You said that you were going to mention the planetary computer, and you didn't. I'm just kidding. Okay, so now we have 15 minutes of Q&A, and thank you for all the speakers to be on time, so that makes my job very easy. If you are online, please pose your question. I'm going to ping Lucas for questions online. Since I'm moderating, I'm going to make the first question. Listening to this session, it seems, Rhiannon, that you are really good at inspiring what is possible, and also seeing that it's already being used. It's the top use case of Earth observation is crops, right? It's already at the top of the pile. With your work, Hamid, you're telling us, yes, it is AI is a great mix in the pod. It's a little bit more work because it's not to adopt, but it's to adapt, which is more work than just using it, right? And then Raul is telling us that, hey, we are here to help with the skills because we realize people that might not have the skills. Hearing to you 3, it seems that, okay, everything's fixed, we can go home. Clearly, it's not the case. What's broken? What can we do better?
I love to be critical. It's a great question. I think I was joking, our little peanut gallery back there, we were kind of chatting in between the sessions, and so much of the technology is very exciting, but I think what is really broken are the coordination mechanisms, the people mechanisms, honestly, where we can sit in a room like this today, many of us knowing each other, running in similar circles, and be duplicating and creating a lot of what I'll call similar efforts, if not same efforts, instead of trying to figure out how can we work together, right? Instead of designing our own approaches in a silo and then shopping it around and seeing who likes it or who wants to build on top of it, how about reversing that paradigm and actually starting with what's out there and how can we incrementally actually build on that instead of just doing it for our own motivations? To be fair, that is not a food security specific problem. That is a problem, I think, in kind of technology for development writ large. But for me, a lot of it comes down to coordination mechanisms, incentives, and where I like to focus kind of my thinking around the art of the possible is really on kind of the business models behind things and how can we get more creative there, because we're lagging so much when the technology is rapidly advancing and we're not keeping up when it comes to that kind of piece of it. So
I think Charles would be a good person to be here for this question. But building on what Rhiannon mentioned, I think having the problem owners at the table is key, because we're talking about these solutions, particularly for food insecure parts of the world, but they're going to use that solution or the answer or the insight from these models. And I think working with them from the first stage of the problem design, the solution design, and the basically user interface or user experience is a key piece. And that comes part of the adaptation as well, right? So and going back to the question Rahul was asking all of us in the room, how is it going to change their life, in that decision maker, that policy maker? And are they really benefiting from it? If not, should we change it, or they're good with the existing solution that we have? The answer is not going to be universal. It depends on the country, it depends on the region, but engaging with them is a key piece of inclusivity and I think the design paradigm that we have. Not to mention that the digital divide is expanding. I think all of us know. So we are going to work together to build the solutions, but it doesn't mean that they should not be at the table in terms of design and implementation.
I'll echo exactly what Hamid said, and I think Charles Mange from the Kenya Space Agency kind of answered this question earlier in his talk when he was saying like, yeah, you know, we have these great technologies and we go to the ministries and other people and we have a great session, then they go back to their offices and that's the end of it, right? They don't quite know what to do with it. They don't know what their value proposition is here, like why should they be using this? And frankly, coming from the AI side myself, I struggle with that as well because, I mean, to give you an anecdote, like we thought, oh, you know, we should build this model and that model. The models I showed you, like the Global Renewables Watch, you know, that was built because there's a conflict between land being used for energy or being used for agriculture. How do you resolve that? That's what the Nature Conservancy is. But we were thinking of building all these types of models. We thought this would be great. And then we talked to people in Uganda and Kenya. All these people came into the room. The men sat there, the women sat there. It was very interesting. And we were talking, and the men, you know, all the men were talking, saying, yeah, we need this energy, etc. And then we asked the women, because they hadn't said anything, what do you want? They said, well, water. Water scarcity is our main problem. That's what we need to be solving. And that's not what we were thinking at all at the time. This is a few years ago. So we took that to heart, and that's why we have a place in Kenya and Egypt now, because we want to hear from the people there, like, what are your problems, and then build our models for them. How do we do that at scale? That's my question here.
If it's a literal question, we can also wait for the answers. We probably don't have it in this room. But what I'm hearing is that if data changed the world, this would be a solved problem. But data doesn't change the world. People change the world. People with access to those skills, that data to do big decisions. Also of note, all three of them have offered you help. So reach out to them directly or through Parmes, Katerina, or I, to partner with them, because certainly there's a lot we can do, we can learn from that. Lucas, any question online or from you?
So many, but lots of exciting questions online as well. The first one's for Hamid. Can synthetic data capture the nuances and variances in developing countries as well? So I guess the fear here is right, that like synthetic data may be unrepresentative.
So we actually, in that application, worked specifically in developing countries. We had two examples. One was in Kenya, and one was in South Africa. So the Kenya one, we literally used raw data in Kenya and built synthetic data for that region. And it worked, yes. So if you build it, we didn't build a global one. We didn't assume that will work, or we have the capacity to generate global one. And the South Africa one was a good example because we were already working with the Ministry of Agriculture in Western Cape. We knew the problem they have, so we were working hand in hand with the ministry there. And then they had some good reference data, but we wanted to expand that. So we're like, we are going to use your limited training data, build a good set of synthetic data, which visually doesn't look at all realistic, honestly, don't get me wrong. Some of those images, when you look, you see weird patterns of crops. But we're like, we are going to fit it into the model and see what it does. Maybe the information content is there if visually it's not appealing because you have limited data in terms of ground reference data. And it worked. We could show by evidence using a good set of test data that it definitely helps the model. So yes, in that context works, but you still need some limited data from that region to generate synthetic.
Great, that's good to know. The second question is also for you, and this is, what's the best way to evaluate an agricultural land use change mapping? What criteria, I think, what's a good validation method here?
That's a very good generic question, or a specific in some sense, yeah. Yeah, I think I wouldn't give a kind of off-the-shelf answer to that. It really needs, we need to see really the use case again. I mean, that was my point exactly. We don't want to come up with a recipe for evaluation of generic things. Really, who is the user? What is the scale of measurement? Is it pixel-wise classification? Is it regional? And then you can think about evaluation. I can reference a paper later on if people were interested.
I want to give an opportunity of those in the room to, yes, question?
Very great presentations, and some of them were very AI and machine learning intuitive, which was very happy to see. So my question is, some of the speakers talked about scalable frameworks using AI and machine learning, while some of the models that were discussed had very specific, very detailed data processing techniques, or like formatting the data for machine learning models for that particular region. So my question is, when you're building a model and you're trying to get the best results over a region, so you would do all kinds of like use different techniques that would format and shape your data for a model. Versus if you once you develop that model, if you want to scale it to a different region, all of that detailed tweaking of data, processing data, formatting, and hyperparameter tuning would not be necessary, or would be different for a different region of data. So how can that be scaled?
I think that is a great question. But I also, and you guys might answer differently, but I think we might need to reframe it a little bit on which pieces of that should be scaled. Should it be the model that's then transferred to another geography, or is it more about the approach itself and scaling that with the experts? And what I mean by that is more localized models than really creating these kind of super models, that can readily transfer across Kenya to South Africa to Ghana, et cetera. I think it's more about, to Hamid's point earlier, empowering local experts and or just listening to local experts and offering help and getting out of the way so that the model itself can be fine-tuned for the conditions and the geographies at hand, as opposed to assuming that we need to create it in this context and then transfer it, the same thing over here. That's just not what's been proved out, at least in my experience with AI and ML in food security specifically. I think there are very few features out of imagery that lend themselves to that approach. And I think the signal for us is, don't try to do that always, to take more of a localized approach and really try to fine tune with folks in country, because it might look very different than it would, elsewhere.
To keep the really good behavior of this panel, we're going to stop here because we are on time. But don't worry, the next session is on the same topic, so you can ask the same questions to panel that Lucas will be moderating afterwards. all different questions. So thank you very much for the panelists.
And we have some remaining online questions, but I hope we may get to them in the next Q&A.
Which you are moderating.
Yes,
So you can
yes, I can take a look. So Peter, can you come to the front and take your name tag? So we're actually not going to have a break now. We're going to set up in the next 60 seconds. Yeah. So yeah, we'll quickly set up and then we'll be right back.
I'm going to add a question while you are doing. Rhiannon, are you going to make available your slides?
Yeah. Would love to. I think the powers that be have them.
Okay. Raul? And Hamed, it's outside. I'll ask him.
yes. He's a big open source
Yes. So if anyone is interested in the slides, please reach out.
Okay, great. I'll start to introduce our fourth session. First, I'll introduce myself. For those of you who don't know me, I'm Lucas. I work here in the digital agriculture team at the World Bank. I work a lot on AI for time series, so this is super exciting. We're gonna start with Peter. Peter had a very short commute here, I learned. It was 2 blocks. He works at Impact Observatory, and we're kind of excited to learn what they have in store for us.
Hi, can you hear me? Sure. Thank you. I'm Peter Cairns. I am a scientist at Impact Observatory, and he stole my line about just being 2 blocks down the street. But I came to DC originally and later IO to do science, to contribute towards policy making, providing missing information, particularly for environmental and development purposes. So very, very pleased to be at this workshop. So today we've heard of presentations about agricultural monitoring, yield forecasting, early warning systems, and so on. Here I'd like to highlight something of a preceding question that has been touched on a little bit. Just where are those crops, those fields that are being monitored? And furthermore, where are they situated? What surrounds them? In order to answer that question, you would likely end up consulting a land use land cover data set. A land use land cover map, like the one you see on this slide, essentially shows what lies where, when, usually in terms of some taxonomy, so categorical. So what information would you be able to find? What is the state of the art? More likely than not, your search would lead you to one of a handful of data sets, likewise produced by one of a handful of national governments. These data sets are often of good quality, but do have a number of shortcomings or constraints. Their production is semi-manual typically, meaning that they are expensive, resource, and most importantly, time-intensive to create. This in turn means that there's a long delay between the period of time being mapped or monitored and the release of the actual data set. For example, as of today, the most recent iteration of USGS's National Land Cover Dataset, the NLCD, represents the year 2019. Furthermore, these data sets are typically limited to national territory, at most, and fairly coarse in spatial resolution. The NLCD covers only the continental United States at 30-meter resolution, and global maps, if they're available, are even coarser at 100 or more meters a pixel, typically. Because of discrepancies in taxonomy and coverage, it's very difficult to compare different data sets or utilize them in concert, a theme of today a bit. Monitoring of change is likewise an afterthought in terms of both the taxonomy employed and the length and density of any longitudinal data that are available. In 2021, Impact Observatory created and released the world's first AI-powered 10-meter resolution global map of land use and land cover. Subsequent work has yielded a time series of global annual maps dating back to 2017, all produced using a consistent methodology and deploying a 9-class taxonomy which includes cropland. So every 10 meters to a side square of the surface of the Earth every year is ascribed one of 9 classes in this data set or these data sets. These maps avoid some of the pitfalls of their predecessors. The generation process is fully automated, removing the bottleneck of manual intervention. It is also up to date, with new satellite imagery ready to be mapped just days after capture. Coverage is global, and the resolution represents a major improvement. Some independent analysis, has identified IOs as the most accurate land cover data set. All years of data are free and readily available to the public, touching on another theme, via a number of distribution channels like the Esri Living Atlas, the AWS Open Data Registry, and Microsoft Planetary Computer, as well as IO's own web platform. The keys to doing this were machine learning and cutting-edge cloud computing infrastructure, and I'm going to lob a little jargon at you, but it'll be over quick. We use end-to-end cloud processing, so everything, all of the files, all of the execution, it all happens in the commercial cloud. We use associated technologies like cloud-optimized geotiffs, stack architecture, and so on. The processing is scaled with the most current technologies, Docker, Kubernetes, so on, which allows for our model to be trained on huge volumes of imagery and hand-labeled pixels, which you can see there. Now, why is all of that important? Because all of our infrastructure is fully scalable, we are able to apply our model to every single image captured by Copernicus's Sentinel-2 constellation, which, for reference, images the entire globe every 5 days. This yields a dense time series of land use land cover maps everywhere in the world and all the information that contains. So we have a big screen here, and a sharp-eyed observer might be able to recognize this sequence of satellite images, and the corresponding maps is showing the area around Madison, Wisconsin. You can see the lakes in the isthmus just in the upper right. As you can tell, the maps and the land cover itself change over the course of the year. Most obviously in the leftmost image, it was March. The area was still covered with snow. It's Wisconsin. But normal seasonal fluctuations are also captured, subtler variations between the later images. We are able to retain the time series itself, as well as distill all the model outputs from the year into an annual consensus map on the far right, which represents the overall land use land cover on balance across that year. This is the basis of that annual time series I've been talking about. That distillation step, for the record, is important. Borders on some of the issues or challenges that Hamid was just talking about. At a given point in time, the actual ground cover may be occluded by snow or water, or the satellite blocked by clouds. We also have to filter out artifacts caused by imagery anomalies, haze, shadow, so on. More fundamentally, land cover presents differently over time. Fallow fields were mentioned earlier. Is an empty patch of soil simply a barren field, or is it an agricultural plot outside of the growing season? Considering multiple looks over time is critical for accurate characterization of what is happening on the ground, even at just one moment. But perhaps even more significantly, long-running, consistent time series of maps allow us to explore change over time. Each of the images shown here on this slide displays only a single class from our taxonomy, with the different colors representing the extent of that type of land cover in different years rather than different classes. But even this simple sort of coarse visualization can be revealing, so I'm going to spend just a moment explaining what we're seeing here. The most straightforward example is in the lower right, where we see forest cover in Bolivia, trees, in 2 colors, light green for the before image, the before year, and dark green later. Dark green is on top, so where there was forest in the after step, you can't see the earlier time step. However, there's obviously a big gap in the middle. What does that represent? Well, the before and after, what happened in between was a series of wildfires in California, which denuded that section of the landscape, and which you can see prominently, clearly, with a high level of detail here. In the upper right, it's a similar example, maybe a little bit less dramatic, but we're looking at cropland this time in Bolivia. The dark brown layer on top is the first time step, and the light beige layer below is the second time step. The beige is a little bit harder to see than the bright green over there because we have a more diffuse change happening over time, but anywhere you can see beige, that's agricultural expansion. That's cropland at the second time step that wasn't present at the first. And the last one I'll touch on in the upper left, here we see built area in Egypt. This is actually east of Cairo, New Cairo City. And instead of just two time steps here, we have the built layer from each map or each year in our annual time series, with the darkest representing the earliest year and the lightest representing just last year. And so in a single image here, you can see the trajectory of growth, the starting of construction in different areas that can all be synthesized into a single image. It's a simple example, but even such a heavily reduced, simplified, sort of distilled representation of the data can tell you a story that seems like it should be obvious and seems like it should be easy to find, but it isn't necessarily if you don't have this type of time series data available. And again, the distinction between this mapping process and its predecessors is that we can generate such maps and time series for any country in the world. So, of course, here we see the country of Kenya as of 2022. And I'm going to point out that image in the upper right. There you see agriculture in orange, built area in red, and they're pressing right up against the edge of trees in green. Those trees represent the Mount Kenya, or fall within the Mount Kenya National Park, which is why there's such a clear demarcation there. This is something that these land use land cover data sets have to offer as a value add, you could say, or as additional information beyond just crop mapping. You can see what the context is, you can see what the other land cover around it is. Furthermore, you can see this changing over time. So if you consider the example on the last side, agriculture in Bolivia, or agriculture anywhere, often you'll see agricultural expansion. What type of land cover is that expanding to? In those cases, it was forest, primary forest, being converted into agriculture, and actually those images understate the situation because a lot of that area was being converted into pasture instead, which would show up as grassland or rangeland in our maps. Further down the chain, you can see a different transition where cities expand and they begin to eat up the cropland surrounding them or on the periphery. And so that's a story that can be told with this type of information. I should add that this map of Kenya is from 2022, and it represents our annual map, and it was available just a few weeks into this year. The annual global 9-class maps I've talked about so far have all been made freely available. Impact Observatory is also developing some new data products offering additional information, and these are distinguished in two main ways. First of all, much of this additional detail is derived from disaggregation of those base classes, resulting in a richer, more descriptive taxonomy. So I'll move through these quickly, but in the upper row you can see 3 images showing an area in Mozambique, a satellite image just for demonstration purposes to show you where we're looking at. In the center, the appearance of that area in our annual 9-class map, green trees and pale yellow rangeland, meaning grass or scrub. And then on the far right, a much richer, much more detailed or nuanced version of this, which is differentiating between dense or closed forest and open or more sparse forest, and also denser vegetation in a scrubland type area or sparser. This is useful for ecosystem identification, habitat demarcation, landscape management, that type of thing. The lower row, it's obviously a very different context. That's New York City. You see the same 3, the 9-class map. And on the right, you can see those same disaggregations, but also denser, more and less dense urban area or built area, which corresponds to higher or lower levels of impervious surface, which has its own consequences for heat island effects, water runoff, and that kind of thing. These are not the only disaggregations we're pursuing. So research undertaken for IFPRI under the aegis of CGIAR focused on identifying different types of crops in small holdings in Kenya. And you can see an example of the results here. There are yet other dimensions along which cropland can be disaggregated. Related research focused on separating rain-fed from irrigated agriculture. All of this was accomplished using the same 10-meter Sentinel-2 imagery as our other maps, meaning the same global coverage and short revisit time are available for any analysis of this type. Impact Observatory has also leveraged that same in-house infrastructure and expertise to generate data sets outside of land use land cover, such as a quantitative Earth observation-based index of biodiversity intactness, which features on UN Biodiversity Lab, which looks suspiciously similar to IO's Navigator platform. So, from a monitoring perspective, what are the key elements of this mapping system or these data sets? One, the information is timely. The delay between imagery and maps is days rather than years. Two, it's global coverage. You have the same inputs being applied with the same methodology to generate maps anywhere in the world, meaning not only is longitudinal comparison or study available, but comparison between different regions becomes possible. Lastly, general and custom products. The annual data sets that are publicly available can be complemented with other products that can characterize user-defined areas and time periods, which is very important because you might want to look seasonally or compare season on season, year to year, rather than a wet season to the consecutive dry season, and utilize these richer taxonomies. So, one last thing. I would love to hear from members of the audience. What kind of maps are most useful to you for food security monitoring? What taxonomy or classes would you like to be able to see? What kinds of changes are most important to identify in this context? Our research is directly driven by user needs, so we would love to hear just what those are. Hopefully I'll talk to some of you directly today, and you can always contact us by email, as you see here. Thanks for your time.
Perfect on time, Peter. Very good. Next, we're going to have Vivek, who had to travel a bit further than Peter. He's joining us from New York today, got up very early, so we're very thankful for that. He's the VP Data and Analytics at Atlas AI, which is, I'm sure many of you are familiar, but it's a Stanford Sustain Lab spin-off in the broad area of humanitarian mapping. And he's going to talk to us today about ground data label collection in combination with remote sensing and machine learning. Very much looking forward to it.
Can you hear me okay? Excellent. Thank you for the invitation to share a few ideas with you today. It's great to see many old friends in the audience.
We're not seeing the slides yet, so I think...
Well, I'll keep talking in the meanwhile. It's great to see many of you in person, old friends, make new ones, both in the audience and in the community. Among the few benefits of speaking very late in the day are that you've learned a lot from the previous speakers who've gone before you, so thank you for that. And the second is that you could hope to fill in a couple of gaps that may not have been emphasized in the same way, or maybe there's something worth re-emphasizing again. So I'll try to do that as well.
Drag it. No, like manual drag it to that screen. See? What can we? Let's first.
This is a good opportunity, I think, to remind everyone online to keep your questions coming. We still have a couple outstanding from last session, so we'll have a good Q&A, I think, after. But please submit them.
It's not visible.
Still frequently.
Lucas, do we have 3 speakers or 2?
3. The third one is online.
Oh, awesome.
Perfect.
Okay, here it comes. Hard to talk at a symposium that's all about maps and remote sensing, so it's good to have pictures. Okay, so the perspective that I'm going to take is one of someone who's been in the field over the last 15 years collecting field data for a variety of projects, not just agriculture and crop-related systems, but also energy, transport, desalination. And at Atlas, I'm involved with a number of these initiatives, both on the research as well as partner support side. So I'll just say a couple of brief words about Atlas AI as a company, and then spend more time on the role of field data in the particular kinds of Earth observation research that we're involved with at the company. So the origin of our company was actually through a series of academic collaborations in the science space, which is not uncommon. And in the Sustain Lab, when David Lobel, Marshall Burke, and Stefano Ehrman were thinking about how could you link together remote sensing techniques, computer science, and at-scale computing with development economics problems. And so one of the key research questions that they worked on for several years was, can you use satellite imagery and machine learning to generate very high resolution data about where inclusive growth is needed? So here we're less interested in the physical observations or correlates and trying to connect that with the unobservable but still measurable proxies of economic development and growth. So what you see here is a small sample of their collaborative work, not just on the agriculture, so the yield variation side, but also on poverty mapping and vulnerability mapping. Now, this work also doesn't stand all by itself. It's part of a global collaborative community where over the last 15 years or so, there's been strides that's made. But for us, what this meant was that we could bring that to bear on the vision of our company, which is that companies and governments can anticipate and monitor changes to the economy and societal well-being for this purpose of inclusive growth. And so the theory of change that lies behind this vision is that if we're able to monitor the development progress of every community on the planet and then study how the interventions affect changes in the development outcomes, then maybe we can be more strategic and more targeted about the kinds of interventions and decisions that we take to focus on inclusive growth. So very big vision, very ambitious. So what I'm going to show you a little bit about is how we actually do that today. So we've translated that original vision into a wide range of what we call socioeconomic data fabrics. So this ranges from high-resolution population density and settlement maps, as was presented earlier, agriculture, but also socioeconomic indicators like asset wealth indices, consumption expenditure patterns, the location of critical infrastructure assets as specific points of interest, network connections among those assets, and then trying to connect across these through the linkages. And agriculture represents one such sector where the linkages are deeply embedded in our thesis on inclusive growth, especially in relation to vulnerability and food security. So here are some of the organizations that we work with today. The World Bank has been a longstanding collaborator, and I'll present one example of that today. But then also with the UN FAO, a number of organizations that are working at the intersection of energy and economic development, private and commercial energy and telecom infrastructure, nutrition, and then vulnerability targeting and public health monitoring as well. So let me switch to the specific focus on field data. And here I have 3 messages that I want to preview. The first one is that ground data are not created equal. So we need to be a little bit more precise about how we think of ground data, whether for crop monitoring applications or other types of applications. The second one is that we don't need ground data or labels for everything now that some of the advantages and the capabilities of Earth observation have been demonstrated. So we can afford to be more specific about the kinds of labels that we try to go out and collect. And then the third one is that in some cases, we could more directly advance to the measurement of the outcomes of interest, for example, nutrition or economic development, without first having to measure the specific changes in the upstream sectors. So let me start with an example of the 50 by 2030 Data Smart Agriculture Program. This is a multi-stakeholder program. And we have been working closely with one of the stakeholders, the World Bank, specifically the Development Data Group and the Living Standards Measurement Study as part of this program. Here, the goal is to focus on capacity building in a sense. It's to enable country data systems to evolve in about 50 countries by 2030, specifically from the point of how they build up their own capacity to collect data on the agricultural and food systems of their own countries. So as we're trying to think about how do we guide our partners in these country governments to think about what kinds of data do we want to collect, we have to first try to understand what is the right kind of survey that we try to communicate to them or perhaps offer a number of systems on. So here I'm presenting one phase of the research that's been completed. And in this part of the research, we looked at two broad questions. The first one is about sample sizing. What is the minimum volume of household survey data to reach an acceptable level of accuracy for a crop classification algorithm? So lots of loaded terms, even in this research question, right? Lots of in depends, but we wanted to do the research to answer this. And the second one is an interrelated part. How does the approach to georeferencing plot locations actually matter for the crop classification accuracy? So in this work, we looked at maize and non-maize cereal crops only. And for this phase of the work, we looked at data from significantly large surveys collected on the ground in Malawi and Ethiopia. So this is the IHPS 2019 and the IHS5 surveys. So this is a sample size of about 17,000 fields, quite large in terms of what we work with typically in field data for a small region. And in Ethiopia, this was about 13,000, right? So one note here is that as we go through the process or I should say the pre-processing of some of these ground data collection labels, we end up culling a lot of what's been collected in its natural state in raw form, so that the data becomes fit for purpose for being able to analyze it in a machine learning context. So in terms of what do we mean by how to collect the geolocated plots? And so this chart on the left shows a variety of ways in which, as you're going to the field to collect these labels or what's on the ground, you might make some choices in your data collection protocol. Do you sample at the center of the smallholder field? Do you sample at the corner points? Or do you walk around the entire plot? And the question of interest here is, do these techniques matter? Is one better than the other? And so we looked at these techniques in the research and linked them with our machine learning models. And we find in the results on the right a couple of different main outcomes. The first one is that there's diminishing returns to learning. So there's a certain stage at which having more data doesn't necessarily make the model better in terms of accuracy, right? So there's some diminishing marginal returns to that. And the second main outcome here is that the geolocation strategy, how you walked around the field and collected data at a certain point in the season, also makes a big difference. And some do better than others when you have just a handful of data points. And on the other hand, they start to converge if you have the ability to collect a lot of data. So again, this is to say that all ground data are not created equal, and that we really have to be attentive to how we went about collecting that as we think about generalizing the model then in terms of its accuracy and usefulness in a variety of applications. So I'm now switching to a different activity. This is the topic of network systems along with agriculture. And here the thesis is that to understand a little bit more about agriculture, we may have to look at interlinked sectors. So we may have to think about agriculture as a systems problem. So for example, agriculture is a productive use sink for the energy sector. When we think about processing, irrigation, other aspects. Transportation is also a linked sector in that we need to convey the products of agriculture to markets. And so here we're looking at the linkages between all of these sectors. One of the big challenges is that we do not have commensurate data on all the sectors to understand these linkages and causal relationships. In other words, the data don't exist at the same resolution, measured in the same place, at the same time, with the same purpose in mind. And so we may have to go back upstream and build these data sets using remote sensing and Earth observation techniques to be able to then answer those relationships and questions. So one of the emerging outcomes of this kind of work is that we often use rule-based models and don't depend on learning to be able to build those precursor products in these ontologies. So I should say a word about that ontology in the sense that this is a logical classification of the various indicators that we're measuring. And many of the precursor indicators or classes don't specifically need learning or labels. So we are able to very quickly, using at-scale, planetary scale models to compute on the rule-based indicators and then focus the in-field data collection in a very targeted way. So this is another example of where in that ontology, along with land use and land cover from a crop point of view, we also have changes in human-built environment. And sometimes by looking at those side by side, we're able to say a lot more about the rate of change in one or the other. And so I know this slide won't show up very clearly because of the colors here, but this is basically showing at sub 10 meter resolution changes in the built environment as it could encroach on cropland. So by looking at the inverse of the problem, sometimes we learn about what's going on in the sector of interest. The next idea that I'll focus on is that sometimes looking at correlates or proxies is also very informative. So what's shown here are 4-week ahead forecasts of tractor utilization in smallholder fields. So by predicting mechanization, we're able to understand the rate of change in agriculture for certain types of crops and for certain parts of the agricultural economy. And in this case, again, ground data aren't created equal because we're actually using telematics on those tractors as the labels for what we're training our models to predict on, right? Another example of this is further downstream on outcomes. So here we looked at the affordability in some of these smallholder communities for energy appliances in parts where there wasn't reliable electricity being offered. And we noticed that, so each of the blue dots here is actually a household that owns some kind of energy appliance. And we found that in some of these PAYGO models or installment payment models, they weren't able to afford paying back their original purchase of those investments. And they tend to be located in these agriculturally at-risk communities. So by also looking at the financial transaction history of some of these communities, we're able to understand some of the recent dynamics in the agricultural sector in those communities. A final example I'll mention here is well-being outcomes in terms of nutrition and public health. So here we are predicting the propensity of a community to have what's called zero-dose children, those children who did not receive certain kinds of nutrition supplements at the right development stage, perhaps even no doses of critical vaccines. And so by connecting these with other types of labels from the field, we're able to sort of understand where vulnerability actually creeps in the community. So here, instead of looking at nutrition from the agricultural system, we're actually trying to look at it through the incidence rates of those communities directly. So again, just to summarize here, in our view, the evolving role of ground data is that these ground data sets can be quite different. We can think about specific data collection for a particular kind of problem before we are able to aspire towards generalizing it. Here we can build in other types of indicators as well from passive sensors that are increasingly being deployed around the world. We're able to link together rule-based models along with learning-based models to approach the end goal faster in terms of the scalability of those models. And then finally, we're able to fast forward a little bit and look downstream to the incidence rates and then build that back into our Earth observation techniques for predicting on the outcomes of interest.
Thank you so much. And our third and final talk of the session comes online from Nupur. I can already see her online. Feel free to start sharing. She's the VP Global Impact and Strategic Partnerships at CropIn, and is going to talk to us about scaling predictive crop analytics for food security. And then we go into the Q&A afterwards.
Perfect. Thank you. Can you all hear me and see my screen?
Perfect.
Great, wonderful. Well, Vivek, I'm actually sitting in Palo Alto on Stanford University campus, so we should connect once you're back this side. But good morning, good afternoon, everyone. Thanks for inviting me to speak today. Really excited to speak to you about the work CropIn's doing as it has direct implications to food security in the context that we've been discussing. We've talked a lot today about the case for Earth observation for food security. We've talked about what the technology can do various applications, and we've seen some examples of how this has been applied, but often for a standalone bespoke project. We've also heard the questions raised about how do we scale this? How do we commercialize this? How do we bring the costs down, the speed up? And so that is what we're busy with at Cropin. And so this is going to be a very practical presentation. I'll start by just talking a little bit about the company and the journey we've been on. And then I'll really focus on talking about how we have embarked on a mission to really productize these capabilities so that they can be scaled quickly and adapted for various contexts and use cases quickly and at a cost that is very much commensurate with the value. So that's going to be my presentation, and really excited to be here. So just to give you a little bit of background on who Cropin is. Cropin is about 12 years old as a company, founded in Bangalore, India, and really began as a company focused on digitization in the agricultural space. I think we all know from working in agriculture how complex it is to standardize and create an ontology around agriculture that allows you to really digitize data from the field in a standardized way. And so that's where Cropin really began its journey 12 years ago, and over time has really started to move into the space of earth observation and AI/ML. Today, we have close to 200 employees across 4 global locations, and our products and capabilities have been deployed around the globe. In terms of who we work with, I think there's 2 clear segments. We work, of course, with enterprise clients significantly at scale. These are private enterprises. We don't work directly with growers, but we have a B2B model there. And we also have done quite a bit of work in the social impact space. And a lot of that comes from the fact that our early investors were very much focused on Cropin as a vehicle for scale of this kind of technology within the social impact space. So our early investors include the Gates Foundation, as well as former CDC, now BII. And most recently, we signed we had a research investment from Google. So really pushing the limits in terms of what technology can do for agriculture. Just to lay the context of what we are trying to do as a company. As we all know, we've talked about this at length today, the technologies to solve for complex issues in agriculture, food security being central, exist today. So we have satellites that are providing imagery at a rapidly growing, both from a spectral and a temporal point of view. We have a lot more that's available now. We have access to different types of other technology, drones, IoT sensors. We have weather stations. We have all kinds of interesting data and technology that are available. So the technology exists, but access to that technology in an integrated way often doesn't. And often the means for the right stakeholders, growers themselves, of course, at the center, but others as well, including policymakers and right from policymakers to private enterprises, often don't have a scalable means to leverage that technology. And so that's where, as Cropin, we feel we're playing in that space. In terms of what we're trying to do 4 things. Our goal is really to help organizations bring the right data together at the right time to answer complex questions and make intelligent decisions. And this is particularly valuable when existing systems are fragmented and essential data is kind of siloed in ways that doesn't allow it to communicate. And so we, of course, as I mentioned, support digitization of agricultural supply chains. 2, we are then able to combine that ground data with data from other sources like satellites, as well as the other sources I mentioned, and then extract insights from that data set through different various methods, including visualization and AI/ML. And then finally, creating a platform for those insights to actually be shared in real time with the right actors at the right level of granularity, with the right permissions and controls. So we're trying to do all these different things at the same time, and that's kind of where the kind of rationale behind our product and technology offering. So this slide here gives you a visual of how the technology is layered or organized. This is the stack, and we call it Cropin Cloud. And it's a very customized farmer stack. So it's really, really very specifically tailored for use cases, a broad range of use cases, but very specifically in agriculture. And it allows for a sort of a modular format. So we have digitization apps at the base layer. We have a data hub that allows us to ingest data from various pipelines in an automated way. And I think I want to emphasize this piece around kind of automation, right? So there's a whole lot of scripts that have been developed to really automate the process with which this data gets ingested and stacked, so that data coming from different sources at different resolutions, at different sizes, can kind of be stacked or layered at the level of an individual plot or a specific geo-boundary in an automated way. So there's very minimal human effort, and it can be done at a speed, a scale, and a cost that really starts to make sense. And then the final piece is the intelligence layer. And this is where the AI ML, the machine learning, the trained models come in. And as I mentioned, all of this is modular. So if someone is looking to just take that intelligence or those crop analytics through an API, that's possible. But if someone else wants to ingest those through field teams that use the app, that's possible as well. I'll quickly just give a sense of the type of data pipelines that are for which are pre-engineered in the system. We have data, as I mentioned, from multiple satellites. So these are all the public satellites, but also through the private satellites through Planet. We have the ability to bring in mechanization data through smart tractors and things like that. So anything that is in the cloud can come in. To the extent that countries have existing databases, proprietary or internal databases, those can also be ingested and layered to create a more rich stack of data to analyze. All of this sits on the cloud, on the commercial cloud. It's on AWS, and so we benefit from all.
Nupo, we lost your audio, I think. Can you still hear us?
No, I can't hear you, Nupur. Nupur, you're muted. Nupur, we can't hear you.
Lucas, are you in the session? There you go. Now she should realize. Or no?
I think Nupur logged out and she's probably trying to connect back.
Yeah, if you can hear us, Nupur, sorry, I tried to interrupt your screen sharing with screen sharing. We lost your audio. We have the visual again, which is great, but we still don't have audio.
You hear me now?
Yes. Perfect.
Okay.
Great.
Perfect. So thank you for that. How long have I not been audible?
We lost you for like 30, 45 seconds, but your enthusiasm didn't budge. It was lovely to see.
Okay, great. That's good. You were just seeing me shake and gesture. Oh, all right. Very, very good. Let me keep going. So let me talk a little bit about the intelligence layer, because I think this is probably the most relevant for the food security discussion. And then we'll start to get a little bit more practical with some case studies and examples. So in terms of the intelligence layer, we have a set of AI/ML models that we have developed that are trained on large data sets across a variety of contexts that are able to do a number of different things, but I'll talk specifically about the crop detection. and the yield estimation models. So we have a crop detection and yield estimation model. These are 3D CNN models, so deep learning models that are able to be transferred and contextualized to a variety of crops and locations with a very quick and light touch hyper-tuning effort is what we call it. And so a very light touch retraining effort that is able to allow us to detect on a pixel by pixel basis what is growing across a range of crops, primarily field crops, and with some limitations, but we are able to detect what's growing on a specific pixel. We're able to aggregate estimated acreage, and we're able to estimate then using yield models, which are primarily based on evapotranspiration rates, the estimated yield for that crop. So this is particularly powerful for the use case around food security. And again, everything I mentioned around the back-end infrastructure allows for this to be done at a scale and with speed that is perhaps unprecedented. So we also have a variety of models that can do plot level detection around crop health. So we're able to combine things like NDVI with information about the specific crop, the stage of growth that crop is in, and the specific context to tell you what does that NDVI raw index, how can it be interpreted around crop health, right? Similarly for water stress, we're able to do a lot of kind of crop health analytics, both at a regional as well as at a plot level. We have models that are able to predict diseases 1 to 2 weeks in advance. These are primarily agri-science and weather-based models, but again, possible to scale across with some work scale across context. We're able to progress what stage the crop is at. And then we're doing a number of things around sustainability, around deforestation monitoring, carbon models, models around stubble burning detection and forest fire detection. So there's a whole lot of detail I could go into here, but I won't. So if anybody has questions, please feel free to ping me now or by email after. But I want to get a little bit practical. I want to share a couple of things with you for a second. So this is a visual, and I think if I have time, I might have a minute or two. I'd be very happy to show you the live dashboard. But this is kind of what our dashboard view looks like in terms of the regional pixel level crop detection. So if we look at a specific, we have a web-based dashboard, and the data, once it's computed, is in the back end, is uploaded into the dashboard. And through this, you're able to see a number of different layers. You're able to first see a kind of land use, land cover layer, and this is the dynamic LULC layer that we are able to see for a given district or given state, or all the way down to the PIN code or the zip code level. What is the classification of land between urban, built up, agricultural and forestry land? We're able to then look at how that land, that agricultural land, is split across various crops. So here in the menu here, you see the various crops that have been detected in these regions. So this is in Maharashtra in India. And so in this particular season, the main crop is sugarcane. And so we're able to see the acreage that is sown with that particular crop and the total expected yield in tons for that crop. And we can go down the list. And this provides a heat map. So you're able to kind of drill down and zoom out. You're able to kind of take out the different masks to see the plots if you wanted. And there's a capability of layering in other external or proprietary databases to layer on top of this. So if we wanted to also, if you look at this visual, you can see how this can be looked at in season for a live season, with periodic updates to get to a more accurate, we get more accurate as we get closer to maturity. But we also have the capability to look at this historically, all the way back until, I think, to the point where we have consistent data coming out of the public satellites. So we can go back to, say, to 2017 for this fairly easily. And so this is just to give you a sense of what this looks like. And then finally, I just want to give you some examples of how this has been used. I'll give you 3 examples, and then I'll pause there. So I think we've seen a lot of uptake for this in the private sector. And so we've seen a lot of companies, this is just one example, use this to be able to really drive their procurement strategy. And so we have a number of millers of various products, rice and wheat, using this extensively pre-season to estimate exactly how much crop is going to be coming and where is the spatial distribution of that crop. And then it also allows them to define where their procurement operations are located and what the ingredient mix is going to be. So in the case of Nigeria, we worked with a leading brewing company that was struggling. Their pain point was volatility in raw material availability and then implications around cost. The cost of ingredients was dramatically affected based on the yield for sorghum. And so they had some capability with some foresight to be able to develop a product ingredient mix that was most cost effective, but it required some advance warning. And so we helped them to analyze 25 million hectares of land across Nigeria, to be able to detect and classify each pixel of land across 9 crops, a variety of field crops, including sorghum, and then estimate and map acreage and yield with an 84% accuracy. There was some
I'm so sorry,
validation.
but I
guys-
think, if we need to wrap up here to allow a bit of time for Q&A still. So say your
Sure.
last 2 sentences, and then we'll go into the Q&A.
Perfect. Cool. So I'll just wrap up this one. I think it gives a good sense. But with this example, I think there's a tremendous amount of applications in terms of food security, in terms of advanced prediction on a live basis, particularly in contexts that are So I'll pause there. That's it. So thank you for that, and I will stop sharing.
Thank you so much. So, Q&A. I want to start off with one of the online questions, and I think it's best for Vivek, actually. It was about differences. So the question was, can we do also inequality mapping instead of poverty mapping? And I think that's maybe a good motivating start to the Q&A.
Yeah, I think it's certainly a plausible question. My first sort of follow-up would be, how are we defining inequality? And there's a variety of ways, I suppose. Once you agree on a construct, one could certainly link that to existing data sets and correlates. So in principle, the answer is yes. There might be some genuine concerns about how do you actually measure, validate that, build a statistical model, whether it's machine learning or any other framework, to then confirm the accuracy of your predictions and measure those. But in principle, it seems like a construct that has been studied a fair bit and is doable at scale.
Cool. So with this, let's give it to the room.
Yes, thank you. This is Gitanjali. I am CEO and co-founder of Energy Guru. We are more into hardware for the food security perspective. We manufacture solar dryers as well as robots for regenerative farming. And also we have one solution that can improve the soil fertility. Now, my question is more to Peter. This is about the more use cases, so that I'm hoping to get those maybe addressed through Earth observation. So I think we know that 30 to 40% of the agriculture produce goes waste. So is there any food waste data? I think that I had asked Parmesh as well this morning. If we can get that, the layer, that will be very helpful for us. Food waste data across the world, because I think if we save that produce, I think that will be that itself will solve a lot of food security problems. Then The soil quality data, I think this is a question pertaining to natural farming or the regenerative farming. So do you have any soil quality data which is based on the natural farming or the organic farming? So I think that is something that would help us as well. And the third thing is, is there any soil quality data that is based on the breed of the cattle that is around that area? Like, for example, we know that A2 milk is good for our health. So do you see any soil quality data improved based on the cattle that was around that, like cows or bulls?
Wow, that's a heavy task for Peter. But we'll go one by one. He's taking notes diligently, I can say.
You can always give it a shot. Like you said, in order, food waste data across the world. I'm going to punt on just that first one because food waste, it's 1 or 2 or 3 steps downstream from the Earth observation data that Impact Observatory is typically leveraging. So not that data doesn't exist, but that's not a data set that we're generating. That has to be, we can only tell you about what's happening on the ground, not after harvest and so on, what happens there. Soil quality data, there are remote sensing data sets available produced by NASA, ESA, that are measuring certain qualities, quantitative aspects of the soil. I mean, the most straightforward would be moisture. That's obviously not getting at soil quality. The closest thing that I can give to your question would be the possibility of detection of different types of agricultural practices, which is available through remote sensing. So, for example, the presence of cover crops. You can look and detect turnover of soil. Some places are doing no-till, some places aren't. That's at least feasible within the set of techniques that we use. We have not pursued anything in that direction at this time. For the last item, though, soil quality as a function of cattle. Quality, perhaps not. We have investigated, somewhat incidentally, changes in land cover as a function of grazing animals, so cattle, but also non-domesticated animals, and pointing in the other direction, trying to look at and detect changes in land cover or fluctuations within a single type of land cover, so detections of grazing in scrubland or grassland in Southeast Africa, to see if we can use changes again in this Earth observation imagery to detect the presence, because there were people, a partner that we're working with is interested in, are people bringing cattle across into a conservation area? If they are, what times of year is that happening? What is the impact on the vegetation health? So not the soil in this case, but the vegetation health. And it was interesting that they came to us with that question, sort of agnostic or without any prior conception. Maybe this is damaging to the natural landscape. Maybe this is actually helpful. We don't know. That's, you could say, exploratory work, so there is no published data set that we have about it. But that's an area where there is that direct linkage between what we can see using Sentinel-2 or other satellite constellations and the actual features of the soil and the vegetation there.
So question for Vivek, but Peter, would be good to get your insight. And that paper that you mentioned on the sample size and the quality of like the field boundary ground reference data. So in this case, you had the large number of data, so we are able to see that saturation in model performance. In a new problem, new field, did your team come up with a framework how you would go after that? Because, I don't know, you want to go and gradually add more data? What would you do in a practical sense in a new region and in a new problem for sample size?
Yeah, so that's very much an active question in this process of developing guidance. So for example, if you are a Ministry of Agriculture or National Statistical Office, and you're just getting started on crop type estimation or yield estimation problem, you have this question front and center: how much should I collect during the first pass? And so we do have some follow-on experiments in this case where we broadened it by crop type, because we noticed some sensitivity to the particular type of crop, sometimes even by species. of course, by the ability to collect a representative sample across the agroecological zones within that country. And so here we have actually run some follow-on experiments to address that question. And without sort of getting into too many of the technical details, the short answer is we can get away with less data starting out and actually build a multi-shot experiment. So as we learn from those initial experiments, continue developing the program. Of course, that also helps with many of the issues we've talked about today as a group around capacity building, learning from those protocols on data collection in the field, building up internal skill sets on not just designing those surveys and maintaining those databases, but also being able to run those experiments within those entities as well. So, thanks.
Great. Since we'll have the opportunity to talk afterwards in person, I want to pick the final question from online, which is for our online speaker, coincidentally. Have you tried using your system for kind of climate smart agriculture applications? So the question was about tillage versus non-tillage, but I assume anything, for example, like low carbon rice would also be of interest.
Sure. Yeah, I think we have. So just specifically on the question about tillage, we do have capabilities to detect tillage using remote sensing, and we also have the capabilities of detecting soil and canopy moisture levels. So it would be very interesting to put these two together and to find associations and correlations. So we're always looking to find interesting ways of bringing our capabilities together to solve for problems. So to the extent that someone who has ideas of how this can be applied, please reach out. I think, we have a powerful platform to provide insights. And then, of course, that insight needs to be translated to action through efforts in the field. And so we are not the solution alone. It's just about bringing the technology to drive the insights that drive the action. So, but very, very much looking forward to discussing, I think it's Malika's question on this offline.
Thank you so much, Nupur. Then it's my pleasure to close the session and hand over to Parmesh for our closing remarks, and then we go into the informal part of the event.
Yeah, that's the exciting part. There are some drinks also available. So if you want to unwind after a long day of listening to data, AI, and ML, and want to bond again over data, AI, and ML, there is opportunity there. So it's very difficult to summarize such a rich day. I think we have significantly benefited from perspectives about what Earth observation can do and what it cannot do. What are the new things in which we don't have to do things the way we were doing 3 years back? There is functionality with the AI and ML, which we don't have to start from scratch all the time. And I think these are questions as we go forward. There are questions about how much is the ownership at the local level. Before we start doing this, is it a supply-driven model or can it become a demand-driven approach? There are a lot of questions which are being raised. And as we invest in global public good of this kind, I consider part of Earth observation as a global public good, and part of it is to develop very innovative products and services which will take it to the private good and which will create applications of different kinds. Because public good is more in terms of creating the architecture, the infrastructure, but in terms of converting into products and services, someone else will have to come and play a bigger role there. It's a relay race, if you know the athletics part of it. It's a 4 into 100 or 4 into 400 or maybe 4 into marathon. You never know, because there is a part which everyone has to play to reach there. And if everyone is trying to create foundational data, then it's going to be very difficult to reach the path there. And in the process, the crises will keep on coming, investments will be required, and they will be, not data informed or analytics informed. And then we will waste a lot of public and private resources also. And when we know we are short of resources globally, it's impertinent on us to really optimize the investments which are going there. So I think I've drawn some lessons for us. I'll not summarize each presentation because they're rich in itself. It will take a lot of time to summarize that. So I think we are struggling with the issue of scale. The crisis is so huge. So take that we have, say, 35 or what data showed that there are 56 countries in crisis. There's no time to collect a whole set of ground data there. We have to just harvest whatever data is coming from the cloud or the AI and existing data, which already, I just summarized. I think Kenya should be using data almost on a daily basis, and there's so much data available. But I worked in Kenya. We have 4 investments, 450 million. We created a big data platform and all. Yet I will say that the utilization of data, use cases, we have now 6 there, but it should be higher, and it should be the most data-enabled system. And why I am saying this, Kenya is the place where we have created a digital transformation office within the Ministry of Agriculture. There's a chief data officer in Kenya. So we have a lot of institutional things which people were talking about in terms of ownership. And this is the reason why a lot of things are happening in Kenya, because you see some ownership there of these things. There's someone who is, but yet I feel that we need to find a way by which we are able to do these things in a relatively efficient and fast manner. We can't have a situation where it will take us 4 years to, as you said, learning doesn't have to happen. Learning part has to change a little bit, And then what you said also, you said about learning, there's no point in collecting data all the time, ground data. Every ground data is not equally good. If you combine things, you might come with a very different paradigm of how we will do these things. So open offer, we have so many countries in crisis. We are going to take 5 countries and see whether we can create an EO-based system from day one without collecting any ground data. Let's see what happens there. And we will give you the names of countries, and we will run probably some kind of an innovation challenge in which you have to bring all your top game to work in those 5 countries and see what you come up with. And if we are able to short circuit a lot of this long-worded thing, and we know there's no capacity in those countries to do that, but if we can sensitize those countries which are more conflict countries to use more Earth observation data and use applications and use cases there, it will be just a kind of, it's still a dream, but I think we will have a stretch goal there in terms of those countries there. The second part is, I am not making a case that we have to do everything pronto. We have to build capacity. We have to build medium-term agenda on this, on how Earth observation plus other things can lead to creation of really data-based evidence and decision-making, not only at the policy level, but at the investment level, investments. And then what you talked about there at the end, Vivek, about the inclusive growth models. We are doing country climate development reports in every country. It's going to inform our climate smart investments. If we can factor this data to come more centrally into our country climate reports, then that will change the way the discourse happens between them. We are having a very major dialogue with the countries because of the crisis, both COVID and fertilizer crisis because of Ukraine. People are saying we don't have the same resources to keep on investing in chemical fertilizer subsidies. Is there a better way to look at existing data and to invest differently? And that's where people are saying, okay, should we invest in soil fertility incentives as opposed to fertilizer subsidies? And we are saying, can we pool all the soil fertility fertilizer data which exists on cloud, EO and all, and bring in a common architecture of platforms where countries could use that data to do more targeted public investment on that. Because it is clear that we found in Kenya when we tried to do this, that 38% of Kenyan soil is phosphorus toxic. In fact, it's creating more problems of soil quality than it is solving the problem. So the clear thing is that don't send P of DAP to those 38% people, and that reduces your cost, but also then you can come with other biological amendments and microbes which are from the regenerative agriculture side to do that. So we have to find a way for this not to be a data thing, but this to be a solution finding kind of a way to do things, because people could make investments differently, people could change policies, and people could take decisions differently. And there is a cycle of these things. That is not contingent on the research cycle. That cycle is happening independently. Like we will invest billions of dollars in the next 3-4 years. And then if we are data informed, evidence informed. To the extent we can harvest all the data which exists in this room with the collective experience you have, and pick up some countries where we work together in terms of building this platform which is there, and see what kind of investment would be required, both from the public and private perspective. So I think we are looking for investing in a platform, not jointly. Obviously, GeoGlam has already done a lot of work. We'll have to work very closely with them on this, and we hope that we will develop collaborative partnerships with you as we go forward. We are also trying to do a different way of doing things by launching an agri-food data lab, so that data lab will work with all our governments, clients, and they'll offer them a data coach, data mentor, and a data partner. And so we will come back to you. If you already have domain experience in that topic and that geography, then you are the most ideal partner to become the data coach and mentor. And then we can have a very sustained relationship for at least 3 to 5 years with that country, so that we turn the way the country uses data fundamentally there. So I think this is something Bruno, Lucas, they are working on design of that data lab, and I think they will come to you at some point where they will tell you about what use cases our countries are telling them. And we said it should be demand driven, it should be country owned, and our big danger is that we become so supply driven on this topic. Most data initiatives, I have been part of some of them, are very supply driven. I have to be very, mea culpa about this basically. And I think we have to change that a little bit in terms of really spending some time on doing this. So Bruno and his team are meeting all our teams, and we will meet all our client teams to find out what are the issues people are looking at, and we will really respond to the issues people are looking at, as opposed to saying this is the issue you should look at. But in the process, if we already have analytics which pushes them to think about other issues, we will do that. But not as a starting point where we say we have something already and we're going to dump this on you. So I think this is radically different from the way we have worked earlier. And I would also welcome ideas on, if we have to do this data lab, it's not a World Bank effort, it will be a joint effort of many institutions. How do we do this in a multi-institutional kind of way? But we are assuring you that in the 10 or 15 countries where we will work very intensively, we will bring you onto this platform there. And let's see how it works. And we will learn in the process. And I think this cannot be done in a typical consultancy model in which we work for 6 months, and then it's like, I call this, train and vanish, kind of a model, which is absolutely not sustainable in the long run. We have to really stay with this for a longer period there. So I think we definitely be on the capacity agenda. We are talking with a number of people on developing a data science curriculum in Africa with 100 data scientists who become then your partners. We are also thinking of launching an internship program, data interns, who will work with each one of you and will become the kind of, because we need to bring in, I think we need to bring young blood into this also. I must confess that, we are all reaching that stage where we are all learning more from the young people. And so if we have to bring all the young people into this from day one, I think I am keen to have at least 100 digital interns working across these countries with us and others there. So there is no other way we will be able to do this. And this is to the young people who are in the audience from Maryland and others. We are going to announce something by which you can join. But you will not be working for us, you will be working with that partner, which is going to be the data coach and mentor there. So I think we will create a different dynamics of how we implement that than what we have been doing there. I liked a lot of ideas on geodiverse and synthetic training data sets, which you talked about, and then also the AI functionality, which you talked about also. I think we have to really be on top of this, rather than, again, collect a lot of ground data, which may not be useful, then train that data, then go to AI. So how can we reduce this cycle from a 3-year cycle to a 1-year cycle is very, very important. Because it will become redundant if you don't do that. As someone said, after 5 years, things will change. So I think we have to reduce and shorten the cycles of learning and implementing this and learning on the ground. As I told you right now, that we have about 53 investments now on data and digital. We have 38 countries, and we will definitely call on you to become part of that. Please adopt 2 of those countries as part of your partners. Adapt, whatever we want to do, and we will facilitate that interaction between the stakeholders there. We have convening power, definitely. We will use our convening power to make sure that the friction you have in terms of doing this with governments and others is reduced, and we are able to invest in some ways of doing things which are different than they have been in the past. So I don't want to spend a lot of time, but personally, as well as for all our team, this has been a very important learning process for us, but we are not going to stop at learning. We're going to definitely integrate this into our investments, and then only we can really, the road has to, we have to hit the road on this basically, otherwise this will become just a talk shop. And so we will come back to you on a follow-up. I want to thank my colleagues who have led this whole event. Katrina, thanks a lot for leading this exercise. Julia, thanks for being at the back end of it and doing everything so that every presentation runs spick and span, and for following everything up. Venkat and Ramon, and I must be forgetting someone. Please mention if I've forgotten someone. Sharing on the other side. A lot of people are at the back end who are remote, and they are making sure everything works as well. So thank you very much, and please join us for a networking event now outside. Thank you.
A very small comment for those who are external to the World Bank and you have your little visitor passes. When you leave the World Bank and you pass the security, if you could please drop off the pass. Thank you so much.
Otherwise, we will be prosecuted.